Let us see an example of how to calculate the induced voltage in a DC machine armature. Let us consider a DC machine with an armature winding which is wound for, let us say, 4 pole P equal to 4, and the total number of armature conductors Z equal to, let us say, 1000. The flux per pole phi p equal to 0.04 Weber, and the machine is rotating at a speed n equal to 500 rpm. So, what will be the induced voltage? This is a simple application of the formula E b equal to phi p Z n by 60 into P by A. Since this is lap connected armature, therefore, P equal to A and P by A equal to 1. Therefore, E b equal to phi p is 0.04 into Z is 1000. So, that is 10 to the power 3 into 500 divided by 60, that is equal to 20,000 by 60, approximately equal to 330 volts. Now, if the same armature is rewound as a wave winding, 2 circuit wave winding, in which case the poles will remain same number, that is 4, but now for the wave connection it will be A will become equal to 2. Therefore, P by A will now be 2, and hence this is the for lap connection, E b for wave connection will be E b lap multiplied by P by A, that is 330 into 4 by 2, that is equal to 660 volt. So, the wave connection, the machine will generate higher voltage, but will the power increase? Let us see. The same conductors are connected either as wave or as lap. So, due to connection their current carrying capacity does not change. So, let us say the current carrying capacity is, the conductor is I c, then for lap connection armature current I a, maximum armature current I a will be A into I c, that is 4 I c, whereas for wave winding I a will still be given by A I c, but now A equal to 2. So, this will be 2 I c. So, power for the lap is E b lap into I a lap equal to 330 into 4 I c. Power wave equal to E b for wave connection into IA wave connection, this will be 660 into 2 IC, this is equal to 1320 IC, this is also 1320 IC. So, we see although the generated voltage at the same speed will be higher for the wave connected machine, its armature current will reduce and hence the total power produced as a generator either due to wave connection or due to lap connection will remain same. But depending on the required voltage, we will choose the armature connection, that is if a higher voltage machine is required, high voltage low current machine is required, then wave winding will be preferred. If a low voltage high current machine is required, then the lap winding will be preferred. So far we have seen the effect of field pole only on the generated voltage and torque. However, in a practical DC machine, both the field winding and the armature winding carries current simultaneously. We have seen that the current flowing in the field winding produces a magnetic flux. The same is true for the armature winding. The current flowing through the armature will also produce a flux density waveform, and these two flux density waveform will interact. So, in a practical DC machine, the induced voltage and torque will be due to the resultant flux of these two from these two sources, that is a field flux and the armature flux. The armature flux will modify the field flux waveform to some extent, and this is called armature reaction. Let us look how this modification takes place. So, again let us consider the developed diagram. This is north pole, this is the south pole. The brushes are at these positions. The armature windings are moving in this direction, and let us say this machine is working as a generator, in which case we have seen the induced voltage will be of such a polarity that it will try to oppose the very cause which it is due, which means these currents will try to produce a flux which will flow from the stator to the rotor. Therefore, this will be dot, whereas this will be cross. The field flux density waveform we have seen is trapezoidal. What about the flux density waveform produced by the armature current? It can be shown that the MMF produced by the armature will be of triangular. This is field flux density waveform. The MMF, magnetomotive force, which is given in a closed path by the current enclosed, will be of triangular waveform with its peaks coinciding with the brush axis. Naturally, due to this is armature MMF, AT armature. Due to this armature MMF, there will be a flux which will positive direction, which is from stator to the rotor. This flux will have a zero crossing at the pole centers and will have a expected to have a maximum value at the interpolar region, but at the interpolar region the air gap is very large, and hence there will be a dip in the interpolar region, and the flux density waveform will actually look somewhat like this. So, this is flux density waveform due to armature winding. So, the resultant flux density waveform will be distorted. There will be two prominent effects. First of all, there will be reduction in the flux density waveform on this side of the pole shoe, and there will be an increase, corresponding increase on the other side. As well as the flux density at the position of the brushes will no longer remain 0, but it will shift by some angle. The resultant flux density waveform will be distorted and will be given by this red line. This distortion of the field flux due to the current flowing into the armature is called armature reaction. Now, what is the effect of, let us see what is the effect of armature reaction in the, what is the effect of armature reaction on the induced voltage and torque and etc. We have seen that the voltage induced in an armature coil depends on the flux per pole. Now, the flux per pole due to the current flowing into the armature is due to the field flux and the armature flux. It is to be noted, although the individual armature coils are moving with the armature, however, the pattern of dot and cross currents between the brushes does not change with time. Therefore, the armature MMF and hence the armature flux density waveform are also stationary in space, they do not change, because individual armature passes through the brush, but the pattern between of dot and cross current between two brushes remains always fixed. So, the armature MMF and the armature flux also remain stationary in space. The armature MMF peak coincides with the brass axis and its 0 is usually at the magnetic axis called the direct axis, and therefore, there will be a distortion in the resultant flux. However, if we assume that the magnetic circuit is unsaturated, we see that the net MMF under net armature MMF under one pole is 0, that is the negative MMF at this edge cancels the positive MMF at this edge, and hence if the field circuit is linear, that is flux density is proportional, flux is proportional to the MMF, then there will be no change in the net flux per pole, hence the induced voltage will not change. but in general the machines do not work in the unsaturated region of the magnetization curve. So, if we consider the magnetization, the saturation of the armature and the iron of the DC machine, then we arrive at a different picture. Let us consider the BH curve of the magnetic path of the DC machine. Normally, for proper utilization of the iron material, the normal operating point due to field flux is already in the saturation zone of the BH characteristics. Now, on which if we apply a positive armature ampere turn and a negative ampere turn of same magnitude, we find that the change in the flux density are not same. That is, increase in the flux density due to increase in the ampere turns is less than the decrease. Therefore, what will happen due to same peak armature ampere turns, which is negative on this edge and positive on this edge, will not result in same amount of increase and decrease in the flux density waveform. That means, the while on this edge the flux density will reduce by substantial amount, which is almost proportional to the AT. On the other edge, the increase will not be as much. So, the decrease will be more than the increase. Therefore, there will be a net demagnetization of the field flux, that is, the flux per pole phi p will reduce, and hence the induced voltage will also reduce. This is one problem. The other problem is that we find that the position of zero crossing of the resultant field waveform, field flux waveform is different from that of the zero crossing position of the field flux alone. The brushes are usually placed at the zero crossing of the field flux, but because of armature reaction, the resultant flux density at the position of the brushes is no longer 0. Hence, the coil that will be connecting to the brushes will not have a 0 induced voltage at that time, at the moment of commutation. Hence, during commutation, when we have seen that the coils are shorted, the induced voltage will not be 0 and there will be circulating current and associated problems. This is one disadvantage of armature reaction. The other disadvantage is, even if this is not the voltage induced in every coil, we have found that instantaneous voltage is proportional to the flux density. Because of this increase and decrease in the flux density waveform, the instantaneous induced voltage in a coil will be far larger than their average value. Hence, what will happen is the adjacent commutator segments will be subjected to a much larger peak voltage, which may cause breakdown of the insulation between the commutator segment. Therefore, it is necessary to counter the effect of armature reaction in a DC machine. So, for that we need to find out what is the peak of the armature ampere turns. We know there are total Z number of conductors. So, the total Z is the total number of conductors in the armature. The total number of turns is Z by 2, and if the total armature current is I A and number of parallel paths is I A, then the I C in the conductor equal to I A by A. So, the armature ampere turns can be calculated as Z I C and per pole is divided by P. So, this is the armature So, this is this magnitude. That is Z I A by 2 A P to armature ampere turns peak. In order to negate the effect of armature reaction, this ampere turns needs to be compensated. This can be done by putting adding another winding to the pole face. and then exciting this winding in series with the armature, so that the armature MMF is to some extent cancelled by the MMF produced by this new coil. This is called the compensating winding. It is a pole faced winding which carries a current which is proportional to the armature current. So, how much should be the ampere turns produced by this coil can be easily found out from the formula that ampere turns of the compensating winding should be equal to ampere turns of the peak of the armature into pole arc by pole pitch. Where we have seen that obviously the compensating winding will not be able to completely eliminate the armature reaction MMF, because the pole shoes do not extend over the entire armature surface. In fact, this compensating winding will mostly compensate for the flux in the of the main flux, demagnetization effect of the main flux, but it will not be able to compensate all the flux in the interpolar region. For that, a separate arrangement needs to be used. So, the arrangement along with compensating winding can be represented like this. Let us say this is the DC machine, these are the brushes. The compensating winding are to be connected in series with the brush. While the field winding so compensating winding is placed on what is called the quadrature or the interpolar axis q axis of the DC machine, while the main flux is on the d axis. Once the compensating winding is in place, it will cancel the armature, mostly the armature MMF flux in the directly under the pole, but it will not compensate completely the MMF at the interpolar region. Therefore, the armature MMF with compensating winding will look somewhat like this. This was the uncompensated armature ampere turns. If this is the extension of the pole arc, then ampere turns in this region gets compensated, but not outside this region. So, the ampere turns produced by the pole faced compensating winding will be in opposite direction and we will have a peak value same as this. If this magnitude is a peak, then the ampere turns produced by the compensating winding will be into pole arc by pole pitch. That is, this is pole arc and this is pole pitch. Therefore, this amount of armature MMF at the interpolar region will still remain uncompensated and hence the flux density waveform shows the flux density waveform due to the field flux, the result remaining armature reaction MMF after compensation by the compensating winding will be of this form. Hence, there will be small armature MMF flux produced in the interpolar regions, and the resultant flux density will still show a shift of the what we call the magnetic neutral axis, that is the flux density, the position where the brushes are normally kept will not be 0. This will give rise to some problem in commutation, which we will discuss in more detail in the next class, and we will see how to use interpoles to cancel this remaining ampere turns at the interpolar axis. Before we end this discussion, let us look at a practice which is sometimes followed in a DC machine. We have seen that due to armature reaction, the magnetic neutral axis shifts. Accordingly, sometimes a shift is applied to the brushes. That is, if we look at the DC machine cross section schematically, just for simplicity take only a 2-pole machine. Originally, this is the interpolar axis and brushes are supposed to be in this position. However, if there is a brush shift of beta given, then the actual brush position will be this. Now, the current direction in the armature will change accordingly. These currents will be all dot, and these will be all cross currents. So, we see that the armature conductors these are all cross currents, these are all dot currents. the field flux is in this direction. However, the flux produced by the armature conductors in this angle beta is in opposite direction to the field flux. This is called the demagnetizing flux due to brush shift, and if there are total z number of conductors, the demagnetizing ampere turns, so z divided by 4 pi into 2 beta I c, that is the demagnetizing AT demagnetizing. So, due to brush shift there will be a demagnetizing ampere turns, that is the total ampere turns, this is the AT demagnetizing, and this is the what is called the cross magnetizing ampere turns. The rest of the armature conductors will contribute to the cross magnetizing, that is the ampere turns that produces a flux aligned to the quadrature axis, while the demagnetizing ampere turns are ampere turns that produces flux which are aligned to the direct axis, that is in the field axis, and are in opposite, produces a flux that are in opposite direction to the field flux. Therefore, if a brush shift is applied, then it is necessary that number of field turns be modified accordingly in order to counter the effect of demagnetizing ampere turns due to brush shift, and the field number of turns can be, the field ampere turns necessary should be equal to the demagnetizing ampere turns produced by brush shift, which is given by this formula, where I c equal to I a by ampere, the number of parallel paths. So, in summary we can say that due to armature reaction, the armature reaction is due to the current flowing into the armature winding. The current flowing in the armature winding produces a armature ampere MMF waveform, which is triangular in nature. The peak of the triangular waveform is at the quadrature axis, while the zero crossing of the ampere turns produced by the armature is in the direct axis, that is directly under the pole. Due to this armature reaction MMF, although the actual armature conductors rotate in space, the armature MMF is stationary, because the conduction pattern of current between two brushes does not change with time. Therefore, the armature MMF waveform and hence the field produced by the flux density waveform produced by the armature current remains stationary in space. Now, the effect of this armature MMF is that it produces a flux density waveform which has zero crossing under the poles, but its peaks are at the interpolar region. But since the interpolar region has larger reluctance, the peak usually occurs somewhat before that, and hence it tends to strengthen the flux density or increase the flux density at one end of the pole shoe, while reducing it on the other end. please note that the end at which the flux density waveform will be increased or reduced will depend on whether the machine is working as a motor or as a generator, and they will be in the opposite direction in motoring and generating mode. Now, if the machine is operating the unsaturated region of the magnetic circuit, then the net increase in the flux per pole will not change and hence there will be no change in the induced EMF. However, most practical machines are not operated in the unsaturated region of the magnetic circuit. Because of saturation, the decrease in the field flux density will be more than its increase, and hence there will be a net decrease in the flux per pole, and due to armature reaction the induced EMF will reduce. Not only this, we have seen that due to armature reaction there will be flux density at the interpolar region, while the flux density due to the field flux alone is 0 at the interpolar axis, and hence the flux density at the geometric neutral axis where the brushes are placed will not be 0. This will create problem during commutation. Hence, it is necessary to compensate for the armature reaction flux produced by the armature current. This is normally done by using a compensating winding. A compensating winding is a pole phase winding and connected in series with the brushes. However, a compensating winding can compensate for the armature ampere turns which are directly under the pole shoe, but as the pole shoe does not extend over the entire armature periphery, the compensating winding can compensate only a part of the armature reaction flux. The armature reaction MMF directly under the interpolar axis cannot be compensated by the compensating winding. For this purpose, a interpole is used. The effect of the flux density at the interpolar axis and how to compensate it using interpoles will be discussed in the next class. Thank you.